Hello everybody, I am Rais Ahmed. I am going to teach you power system second, for which the course code is EE-701T and is a 4 credit course. 4 credit course means it's a 4-hour course. So now let's have a look on your syllabi for the current semester. The course structure has been divided into 5 units. The first unit deals with transients. Where from these come, what are their causes, and how we are going to deal with your transients. Then after, if you have a transmission line, overhead transmission line, and your receiving end is open circuited, or it may be short circuited, or may be terminated by a resistance, impedance, whatsoever, and we are going to see the result of that on these conditions. The second unit is we are going to deal with their faults. As you know, we have an overhead system and there are various types of faults that do occur in the system, and in faults there are symmetrical and unsymmetrical faults. And then after, we are going to deal with your symmetrical components and their calculations and sequence impedances as well. And in the third unit, we are going to calculate the calculations of fault currents for various faults such as single line fault, double line fault, and for three-phase symmetrical balanced faults. And then after that last, how we are going to limit that is current limiting vectors. In the fourth chapter, we are going to deal with stability, power system stability, transient stability, steady state stability, all those things, critical angle, clearing angle, and at last it is real and real reactive power control. At the end, we are going to deal with load flow analysis, where you have a Y-bus matrix, bus classifications, then after you have load flow solutions using Gauss-Seidel methods, Newton-Raphson methods. For this particular subject, the books recommended are, that is power system analysis. Generally you call it as by Stevenson. Actually it has 2 authors, and the same electrical power system by VD and Corey, and then after it is by power system engineering by Nagrath and Kothari, and at last it is CL Wadhwa, electrical power systems. So let us start with unit first, transients in power systems. As you know, transients you may have heard, as you may have studied in your control systems, transient period. And I mean to say, when we change state of the system, that particular period is known as transient period, and the response of the system or a particular circuit in that period is a transient. Now let us start with introduction. This transient phenomenon is actually an aperiodic function of time, and the second property of it is it does not last longer. As it has been shown, it is from few microseconds to 1 second. Now the first one, aperiodic function of time. As you may be aware about it, aperiodic means non-periodic or non-cyclic, or you can say it as not recurring at regular intervals. As it has shown in the diagram, as you can see it is just like this. If it has been a periodic function, then it would have been like this. It had been 0 to pi, then pi to 2 pi, and so on. So it is an aperiodic function of time. And the second one is the duration of this, for which the last is very insignificant as compared with the operating time of the system. What insignificant means? Suppose you are switching on a fan or a bulb. Now the time period, suppose in the evening you are switching on your bulb and it is going to last for 4 hours. And if you are going to compare this transient, which is only up to 1 second, it is very insignificant as compared to 4 hours of operating time of a valve. No doubt, the duration of transients is very small, yet they are very important because depending upon the severity of these transients, the system may result into blackout in a city, shutdown of a plant, fires in some buildings, unusual power cuts. These are the results of transients. How they are going to happen? Because during transient period, the resultant current and voltage may momentarily be relatively high. Also, the system is subjected to greatest stress from excessive overcurrents and over voltage. Now, generally, power system is considered as made up of linear impedance elements of resistance, inductance and capacitance. As you have already stated in your previous semester, when we model transmission line, it is actually what? It is actually a resistance and inductance and capacitance. If it is a short transmission line and it is only resistance and inductance, and it is a medium transmission line, then capacitance is added, and if a long transmission line, then there are all 4 elements R, L, C, G. Now, during the operating condition, this circuit normally remains energized and carries load until a fault suddenly occurs. Now, this fault then corresponds to the closing of circuit breaker or switch, or it may be a fuse. Obviously, whenever there is a fault, there is a rise in voltage or rise in current depending upon the type of fault, and simultaneously we have a relay which gets energized, we send a signal to a circuit breaker, and the circuit breaker do its operation and it isolates it from the faulty section. The healthy system is being isolated from the faulty section. Now, when this healthy system has been isolated from the faulty section, now there will be new distribution of currents and voltage because a lot of section has been isolated. So this redistribution of current and voltage is accompanied in general by a transient period during which the value of currents and voltage rise, as it has been already, as you can see it in slide. This redistribution of currents and voltage, I mean to say that whenever there is a fault, after the fault the circuit breaker isolates the healthy fault from the faulted one, then after there is a redistribution of currents and voltage, and that is the reason of the transient. The time taken from this, whenever there is a fault and after when it has been recovered from of redistribution of currents and voltage, that period is transient period, and during that period there is a rise in voltage and current. Now let's talk about the redistribution. What is this redistribution? Why it is taking a little bit time? As I have already mentioned it in slide, redistribution of voltage and currents cannot take place instantly because generally there are two reasons. As you may be aware about electromagnetic energy and electrostatic energy. The storage is being owned by 1 half of Li square and 1 half of CV square. Now, if we talk about electromagnetic energy, as electromagnetic energy, storage is related with inductance, because whenever there will be inductance, there will be storage. This inductance opposes the change in current, which is its inherent property, because the property of inductance is to oppose the change in current. So whenever there is a fault, so there will be a change in current. Obviously a part has been isolated, that current will take a new value, but this inductance present in the system will oppose that change. Similarly, in case of electrostatic energy, the property of the capacitance is to oppose the change in voltage. As the circuit has been already isolated, there will be a change in voltage. This capacitance, which is already in the system, will oppose the change in voltage. So these two parts, electromagnetic energy or electrostatic energy, which is already stored in the inductance and the capacitive elements, which is being formed in the transmission line, they will oppose these two quantities. Now, as they will oppose, therefore they will take some time to attain the new value. From the circuit is being isolated and attaining a new value, this will take a certain time. That has already, if you can check, as it has already being mentioned in the slide, as the distribution of energy following a circuit chain takes a finite time. This finite time is called a transient period. So the transients remain in the system during this transient period. That's exactly what I was explaining you, that this redistribution of energy now will take a little bit time. It may be in microseconds, milliseconds, or 1 to 2 seconds. That is period is called a transient period, and the transients remain in the system during that period. Then after they die out. Now there is a point, that is CTM, commit to memory, and you can note it down as well. Till now what we have discussed, it is clear from the discussion that in order to have transients in an electrical system, two conditions are necessary. Either inductor or capacitor or both should be present, and second one, there should be any switching operation or a fault. I am repeating. From the discussion, it can be said that in order to have transients in an electrical system, the following requirements should met. Number one, either inductor or capacitor or both should be present. The second one, there should be any switching operation or a fault. Now how these two, because if you talk about resistance is not a storage device. So if there is a change in voltage, that will be instantaneous in resistance. But if you have an inductance or capacitance in the system, they take a little bit time, which I already mentioned. So now let us move to next slide. It is causes of momentary excessive voltage and currents. How there is a rise in voltage and current during that particular or for a small period of time? There are various reasons. Now the first one is lightning, number second is switching, third is short circuits, and fourth one is resonance conditions. If we talk about the first one, lightning, as you know, lightning is actually an electric discharge which take place in clouds. And if we don't have an if we don't have an overhead ground wire that is at the top, what you may have seen on the top of the tower, then what is going to happen, that lightning is going to strike on a transmission line, and it is going to rise in voltage and rise in current. And that, as you know, lightning remains for a small period of time, and that may be the one reason. And obviously the rise in voltage and current is very large, and it may damage our system. Second one is switching. Switching means whenever there is any operation in this power system, suppose we are closing our circuit breaker, we are opening our circuit breaker, we are suddenly throwing our load or whatsoever, that is related with your switching operation. When we operate a circuit breaker or an isolator or any device, a load is being thrown away from your line. At that time there is also a rise in voltage and current depending upon your switching operation, whether you are adding your load or you are leaving a part of, or you are isolating a part of load. Number third one is short circuits. If it may be an, obviously there is an, in India there are overhead transmission lines. Short circuits may be, it may be line to line, line to ground, or there may be a fall of tree on it overhead transmission line, colliding of vehicles with poles, there may be colliding of electric wires, and that is related to the short. And then obviously there is a rise in current in case of short circuits. And the fourth one is resonance conditions, as you may have studied in your basic electrical engineering, resonance conditions, where there is a maximum value of current during that period, because in the denominator is only, it is not Z, it is only R in the resonance condition. Now, out of these four, lightning and switching are the most common and usually the most severe causes. I am repeating, out of these four, lightning and switching are the most common and usually the most severe causes. The most damage being done to the system, power system, is by first two. However, transients caused by short circuits or resonance conditions usually arise as secondary effects, but may well lead to the plant breakdown only in case of extra high voltage lines. Extra high voltage lines is 400 kV, 765 kV and above. But the most important is lightning and switching. Let us move to the next one. Types of system transients. Now there are three types. Before that, I want to mention here, it is dependent on the speed of the transients. The classification depends upon the speed of transients, and depending upon the speed of transients, these can be classified as surge phenomena, that is extremely fast transients. Second one is short circuit phenomena, medium fast transients, and the third one is transient stability, slow transients. We are going to discuss them in detail, as these all types depend upon the speed of transients, as it has already been told to you. So let us move to the first one, surge phenomena. The surge phenomena is caused by lightning and switching, as it is the most severe, as It has already been this extremely fast transient. This is the main cause of this surge phenomena. That is extremely fast transients. Physically, such a transient initiates an electromagnetic wave traveling with almost the speed of light on transmission lines. This generates an electromagnetic wave which is usually called as surge, and they travel at a speed of light, that is 3 into 10 raised power 8 milliseconds. Now, as these waves travel along the line, the reflection at the open line and or at transformers which present high inductance leads to multiplicative effect on voltage build up, which may eventually damage the insulation with consequent short circuit. Now, a circuit has been shown. If you see, this is our generator side, then after is a transformer, and this is your load side. This is a transformer. As you know, transformers usually have high value of inductance. Now, what happens whenever there is a transient in the system? Suppose it may be on your load side, it may be on your transmission line. These transients or the traveling changes into surges or discharged to ground via lightning arresters. Without the initiation of the light short circuit, they are protecting the equipment. I will explain this. Suppose we are changing the state of the system here. Suppose there is a short circuit or a load is being thrown out. So now what happens? There will be insertion of transients here. So as we have connected a lightning arrestor here, as soon as there is a rise in voltage or surge in current or voltage, this will come into play. Normally it acts as an isolator, that is lightning arrestor. Whenever there is a surge of rise in voltage or rise in current, it will activate it and they will go to ground, and this will protect this system. However, if there is a change in here, suppose there is a short circuit or any surge, before affecting the generator windings, they have to deal with transformer winding. As already transformer windings have high value of inductance, that will protect this generator. This inductance will oppose that transients and it will protect the generator, which is very costly. And there is a diagram as well. This waveform, that is VTR, transformer terminal voltage, and VAR, this one, that is arrestor terminal voltage, and this is original surge voltage. Now what happens? Suppose here is a change in the state of the system. It may be a short circuit, it may be load thrown off, or whatsoever, lightning whatsoever. Whatever, there is a rise in voltage. You can see this, just like this. Now, this is transformer terminal voltage. Now, see this one now. See this surge. Surge is this rise, sharp rise. Now, see the operating terminal voltage here. It is touching 400, which is 380 suppose. Now, if it would have not been in the system, a lightning arrest, what was going to happen? There was a rise in voltage that was about 1000 kV. your operating voltage was less than 400 kV. So obviously this was going to damage your insulation, which may have lead into short circuit, blackout, or in case of fire, it may be a source of fire. If there is an insulation breakdown, there may be short circuit, it may be the cause of fire. So this lightning arrestor operates here, and what it isolates this, the original curve. It isolates this one, and it is being suppose it has been here in this, it gets isolated, and the system remains healthy. Now the next one, short circuit phenomena. Now, as you people are aware that more than 50% short circuits take place on exposed overhead transmission lines. Why? Because of insulation failure. It may be at the insulators or towers, or by birds, or falling of trees on overhead transmission lines. Or there may be other mechanical reasons. Now, whenever there is a short circuit, these short circuits, we generally classify them into symmetrical three-phase faults or unsymmetrical faults. What is symmetrical three-phase faults? When these all get in contact, this R, Y and P, these three phases. Suppose there is a short circuit, then it is just symmetrical. There will be same change in all the three. That is symmetrical three-phase fault. And the other faults unsymmetrical. Suppose there is a fault between line to line, only Y and P, or only R and Y, or it may be from this phase to ground, or this phase to this phase and then ground. They are unsymmetrical faults. Now what happens? The occurrence of a symmetrical fault brings the power transfer across the line to zero immediately. Obviously, if there is a fault, there will be a rise in current and there is a dip in voltage, as already three lines has been in contact. So immediately the power transfer will be zero, whereas in case of unsymmetrical faults, the impact is only partial. Because suppose we have a this phase to ground, only this will get affected, these two will act normally. Suppose as this has been shown already, it has been isolated, these two work normally, and this is open fault, it has been break, it has been shown as breaking, and there is no this fault. Now if we are going to talk about the surges now, the speed of these surges is determined by the time constant of the generator windings, which vary from a few cycles of 50 Hz wave for the damper windings to around 4 seconds for the field windings. Obviously there is a time constant, that is why these transients will be sufficiently slower than the surge phenomena, because time constants of transformers, generators are being added to this. That's why they are in the second category. The short circuit currents may attain such high values that if allowed to persist, they may result in thermal damage to the equipment. Obviously, whenever there is a rise in voltage, as I will give you a simple example, you can check at your home. If you have a stabilizer 0.5 kV or 1 kV, whenever you are going to increase the voltage from more than 220, you can see there is a movement in the transformer, just like a vibration. That that is called as stress. If there is a more rise in voltage or rise in current, there will be a thermal damage to the equipment. For that purposes, reclosing circuit breakers are therefore used. Reclosing circuit breakers are a little bit different from normal circuit breakers. What they do, they automatically close the switch periodically to find out if the line has been recovered, then the circuit get activated. If the fault continues for some time, then of course the breaker has to open permanently. Next, third one, transient stability, or we can say slow transients. Whenever short circuit takes place at any part of the integrated system, anywhere, there is an instantaneous or partial collapse of the bus voltage of the system. Partial or total. As I already mentioned, if it would have been a symmetrical one, it would have been a total collapse. If it has been an unsymmetrical, suppose line to ground faults, then it would have been a partial collapse of the bus voltage. Now, as the voltage decreases, the power delivered to the system decreases, because power delivered, suppose this is your generation side, this is a turbine, this is your alternator, and this is your transmission line. Reactance of this resistance has been neglected, and this is your load side, which we call generally as infinite bus. The power delivered from this side to this side is being given by VE, this voltage, sending end voltage, receiving end voltage, divided by the impedance as it is in the reactance, and sine of delta. This is power, and it generally operates at 44 degrees in order to give the steady stability limit. Now, as I already told you, if there is a instantaneous collapse of voltage, and there is a decrease in voltage, what happens? If there is a decrease in voltage, there will be decrease in power delivered to the load. So obviously, the more the decrease in voltage, there will be less power delivered to the system. Now, what happens as there is a fault or anything which may cause transients in the system? Now, initially, for some time, the input to the turbine, suppose it's a hydro turbine, there will be flow of water that is going to remain in the system. If there is a surge, this input remains constant for some time, as there is always some time delay for the controllers, so that in order to initiate a corrective action. Now, each generator, this side, each generator is subjected to a positive accelerating torque from controllers, whatsoever you have as a closed loop system. This condition, if sustained for some time, what condition? There are transients and the input remains constant. If this condition remains for some time, it may result in the most severe type of transients, and that are going to lead the mechanical oscillations in the synchronous machine. Now, these transients, these electromagnetic transients, may lead to loss of synchronism for some or all of the machines. As it has been given, only it is a single system, it may be 2, 3, 4, 5 generators or alternators, you can say, they are in synchronism and there will be a loss of synchronism due to these oscillations if this input remains constant, and here are transients. Now, when there is a loss of synchronism of the machines, which implies that the power system has reached its transient stability level. Once this happens, it may take several hours for an electrical system engineer to resynchronize such a system. Also, the rotor swings are quite slow as they are mechanical in nature. Obviously, oscillations are mechanical. It is the source is the rotor. So, at transient stability steady confines that its time period is from a few milliseconds to 1 minute in most of the cases. Okay, this was an introduction lecture. In the next lecture, we are going to start transients in simple circuits. Thank you. Thanks all.